Hi, this video is lesson 2, module 6. So we're going to talk about ionic bonds and kind of how to show those type of bonds with the transfer of the electrons in different ways. So this is the first thing we'll do together. We're not going to do orbital notation, by the way. It's definitely not that hard. It's harder to draw. But what we do is, if I'm going to try to show the bonding between magnesium and oxygen, I want to write out magnesium's electron configuration, which is, and you can do noble gas or complete, it doesn't matter. And then I would write oxygen, which is, okay. So I start with there, and then I want to show both of these electrons are going to go here. Just, in this case, the magnesium wants to lose 2, oxygen wants to gain 2. If it's not perfect like that, you just draw as many of the metal or the non-metal until everyone, the cations will get rid of all their electrons and the anions need to get to 8. So then what happens now is that the magnesium becomes like neon, and I would write the ion below it to show it's not neon, but its electrons are. And then oxygen also becomes like neon, so it gained enough electrons. So that's how I would want you to show electron configuration, ionic bonding. So make sure you show the arrow with the transfer, and then this arrow is representing that what do they then become is what you put on the right side. You can also show ionic bonding with electron dot structures. So if I do that, I draw my magnesium, I draw my oxygen, and then again, it's similar to the last one. I'm going to transfer those 2 electrons, and then what does this then become? What happens is now I have the magnesium ion. I'm going to put that +2 charge on the outside. And now I have the oxygen. And this time, I'm not using the noble gases like I did in the previous. I'm just showing that oxygen had gained those 2 and ended up with 8, which makes it -2. So ionic bonds are, we've talked about this a little bit. If you remember our lab that we did about the differences between ionic bonds and covalent bonds, they are just kind of repeating over and over. Like here, the green are the chloride ions, the blue are the sodium ions. So sodium chloride is made up of really crystals. We call this a crystal lattice. The number of each type of ion has to be so that overall the compound is electrically neutral. So, there's as many negatives as positives, which makes this neutral. Not all compounds are in a 1-to-1 ratio. For example, if you had magnesium chloride, you would have a crystal lattice, and there would be twice as many of the chloride green as the magnesium, the blues. So binary ionic compounds are when you have 2 different elements. Typically a metal is the first, and then a non-metal is the anion. So the metals become cations and the non-metals become anions. So this is just a bigger example of what we were just doing. So we will be just mainly doing this method and this method. So because we have those crystal lattice structures, ionic compounds are really made up of a large number of positive ions and negatives. So what we do is we give the chemical formula for just that lowest ratio, where everything is able to be electrically neutral. Because they're in this repeating kind of grid, That's why there's the ionic compounds, if you remember from the lab, they have high melting points. So they did not melt. They also have high boiling points, and they tend to, well, they're almost always solids at room temperature. When they do, most of them are soluble in water, and when they do dissolve, then they're able to conduct electricity too. So here's that term, crystal lattice. That's the when you see the cation anion all over in 3 dimensions, we call that a crystal lattice. And then this is just showing you the solubility. This, we aren't going to get into quite this much detail yet. We will eventually, but the water molecules will go and pull those cation and anions off of the crystal and put them into water. And then here's just an example of how high those melting and boiling points are. Super high, not high, these are not numbers you could accomplish by using any of the lab equipment that we have. So because we're in those crystal lattice structures, the ionic crystals are brittle. They're hard, they're rigid. If you do try to inflict a force on them, they are not going to like bend. A metal will, the ions will slide past one another, so you can kind of pull metals into wires or hammer them into shapes. But ionic compounds, if you try to do that, it'll just break. And it usually breaks kind of along the wherever they're in the crystal itself. So you don't have to really know the exacts of that, but you can kind of see in the picture in the middle that, you apply the hammer, you push that down, and then you can see like the positive and the negative are going to repel. So it'll break apart. This is just a new term. We know from our lab, and we just talked about it now, that ionic compounds, if they're in aqueous solution, if they're soluble, they're going to be able to conduct electricity. We just call that term for that ionic compound, we call them electrolytes. So if I have, in this picture, the ions, when they're soluble in water, they're going to be loose and able to move about. So you can see that the negative green ions are heading towards the positive electrode, and sorry, did I say it wrong? I said it right. And then the positive cations are going to head towards the negative electrode. And by doing that, you close a circuit, and you will get conductivity that we can measure, or you can use a light bulb or something to kind of show that. So ionic compounds are not electrolytes until they're dissolved in water, or if they're melted, which is really hard, but they do dissolve easily in water a lot of times. So this is just kind of that summary of the properties. And energy, you guys saw, I did the demo of forming the magnesium oxide. Whenever an ionic compound is formed, it's exothermic. There's energy released. And that's because the compound that we make is much more stable than the elements it comes from. So the formation of a bond is going to be exothermic and release energy. And that is where we're going to leave off. There's more detail here that we're not going to get into.